Going to look at a calculator classified under Special Processes at ChemicalEngineeringNow.com, which is called steam reforming. Steam reforming, or natural gas reforming, or what may sometimes be called hydrogen reforming, is an important process to make hydrogen gas from a carbon-rich feed gas. The hydrogen-rich gas produced can be used as a reducing agent in many processes widely used in the petrochemical industry, among many others. There are two main equilibrium reactions involved. The first is the reversible methane reform reaction, in which methane and steam are in equilibrium with carbon monoxide and hydrogen gas. It is an endothermic catalytic reaction which is typically run at 20 to 30 atmospheres and 800 to 880 degrees centigrade over a nickel catalyst. We can immediately note from this equation that higher operating pressure favors the reverse direction and higher temperature favors the forward direction. The second reaction is the reversible water shift or shift conversion reaction, in which CO2 and steam are in equilibrium with carbon monoxide, carbon dioxide, and hydrogen. This reaction is exothermic, and in the reformer furnace it is run under the same conditions as the methane reaction. Just as a side note, there are other important related operations such as methanation, involving the reactions of carbon monoxide and hydrogen gas in equilibrium with methane and steam, and CO2 plus hydrogen in equilibrium with methane and steam. In methanation processes, residual carbon monoxide and carbon dioxide are converted back to methane. It is an exothermic fixed-bed reaction process. It is usually employed after the carbon dioxide has been separated from the hydrogen-rich stream, utilizing amine absorption. Back to the reformer process. The partial pressure equilibrium constant, Kp, is used to express the relationship between product partial pressures and reactant partial pressures. As shown here, the equations can be rewritten in terms of mole fractions and total pressure. As temperature affects the reaction equilibrium, there is a unique Kp value for any specific temperature. These values will be calculated in the online calculator. Since the reformer is a continuous flowing process of limited size and residence time, equilibrium between these reactions is not completely obtained. So in sizing the furnace, a specified approach to equilibrium will be required. In the following example, we will assume a 35-degree approach. Here is an example. A hydrogen-rich reducing gas is to be produced from 754,210 standard cubic feet per hour of natural gas with a known composition. To produce the richest gas possible, the reformer furnace will be operated at 1525 degrees Fahrenheit at the outlet. A 35-degree approach to equilibrium will be assumed, as well as a 2.2 to 1 carbon ratio in the feed. That means every mole of carbon in the natural gas feed will be mixed with 2.2 moles of steam. The furnace will operate at 97 psig at the outlet so as to have enough pressure for the remaining downstream operations. The natural gas temperature is 100 degrees Fahrenheit and the steam temperature is 520 degrees Fahrenheit. The atmospheric pressure at the site is 14.7 psia. The reformed gas will be quenched to 100 degrees Fahrenheit as a method of drying and further enrichment of the hydrogen concentration. We will start with the assumption of 4-inch diameter catalyst tubes with a length of 37.5 feet. We will now input this data into the calculator at ChemicalEngineeringNow.com to calculate the equilibrium constants, Kp, the flow rate and composition of reformed gas at the furnace outlet manifold, the reformer duty, the flow rate analysis of gas off the top of the quench tower, and the number of catalyst tubes required. And here we find our results.